welcome back to my limit series. Today, we will be proving a property of limits. Specifically, the fact that the limit of a sum of two functions is equal to the limit of one function plus the limit of the other. So essentially what we're saying is we can take this sum and we can break it up, finding this limit by evaluating each part individually. Now, in order to prove this, we have to make a similar assumption as we did in my constant law proof. And that is the fact that these two limits, the limit as x approaches x naught of f of x, and the limit as x approaches x naught of g of x, both exist. So we can formally write that as follows. So for f of x, we can say that there exists a real number L. So there exists an L in the real numbers, such that the limit as x approaches x naught of f of x is equal to L. Also, we want to show that g of x, that limit, exists. So we can say there exists, we can say m, which is a real number, and this exists such that the limit as x approaches x naught of g of x is equal to our m. And we can use these assumptions to prove that this equation that I have written here holds. So let's start with our f of x. So this limit means what? Well, using the definition of this type of limit, we can say the following. So this all implies that for all epsilon greater than 0, that there exists a delta. And why don't we name this delta A? Because we're assuming this is true, we know there exists a delta. And delta is also a distance, so it's greater than 0. Such that whenever x is within delta of x naught, the thing it's approaching, in other words, 0 is less than the distance between x minus x naught, which is less than our delta A, that this implies that the distance between our function and our limit, that f of x minus L is less than epsilon. We can do the same for our g of x. So I'll put a period right here, indicate that we're done with this idea. So there also exists an m, right, such that the limit as x approaches x naught of g of x is equal to m. So this implies the following, that for all epsilon greater than 0, again, epsilon is an arbitrary distance, that there exists a delta, and we can call this delta b, such that for all x, right, whenever 0 is less than the distance of x and x naught, which is less than delta b, that this implies that the distance between our function, in this case g of x, minus m is less than epsilon. Now, similar to my constant law video, we're actually going to make a little bit of a change to these definitions. And what we're going to do is we're going to change these epsilons to be epsilon over 2. So this is epsilon divided by 2. And while again this might look like, oh, I'm changing what this limit definition means, we have to remember that epsilon is an arbitrary real number. An arbitrary positive real number, to be more specific. And every positive real number can be written in the form of a real number divided by 2. So therefore, right, it being less than epsilon over 2 still lets it be less than every real number. So now we want to think about what are we trying to prove? And we're trying to prove this, that the limit as x approaches x naught of f of x plus g of x is equal to what? Well, again, if we're trying to prove that we can just add these limits together, that this would be equal to L plus M. Right? And being able to prove this would prove that this addition law holds. So, if we're trying to prove this fact, I'll box that off in blue, because we haven't proven it yet, that what we're trying to show would be this, that for all epsilon greater than 0, there exists a delta, and we'll have to find this delta, such that for all x, whenever x is within x naught, or x is within delta of x naught, that our function, which in this case is this sum, so f of x plus g of x minus the limit, which is L plus M, is less than epsilon. So this statement, we're trying to show that there exists such a delta, such that this is true. So what we want to do is think about what could this delta be? And given the fact what we are assuming, if we want to be able to use this information, right? We want x minus x naught less than delta, right? Or the absolute value of x minus x naught less than delta, to be able to imply that it's less than delta A and that it's less than delta B, right? Because we want both of these facts, that this difference is less than epsilon over 2 and this difference is less than epsilon over 2, to actually help us out. So how can we make sure that we choose a delta so both of these hold? Well, what we can do is say the following. We can suppose that delta is equal to the minimum of delta A and delta B. So therefore, right, if x minus x naught is less than the minimum of them, then it will also be less than the maximum of them, right, because of the transitivity property. So we can suppose this is true. Then, therefore, we get access to both of these facts that we have right here. And why don't we add them up, right? We can say that f of x minus L plus g of x minus m, including absolute values where appropriate, would be less than epsilon. So I'll write down how we can use the triangle inequality in this case. So we can say that the absolute value of f of x minus L plus g of x minus m, and you can notice that I only have one absolute value set here, that this is less than or equal to the absolute value of f of x minus L plus the absolute value of g of x minus m. And as we have previously established, this is all less than epsilon. And so since we just have this one absolute value, we can actually rearrange some of the things. So we instead can write this as f of x plus g of x minus L minus M, right? And this is actually the same thing as saying minus L plus M, this whole quantity, and that's because of the distributive property. And this, by the transitive property, is less than epsilon. So therefore, this limit holds true, which therefore means we have proven the addition property of limits. Now, before I finish this video, there is one more thing I want to go over. And that is the fact that after seeing me prove the addition law for limits, you might be thinking, is there a subtraction law for limits? And, well, let's take a look at that, right? Can we assume that the limit as x approaches some x naught of f of x minus g of x, is this equal to the limit as x approaches x naught of f of x minus the limit as x approaches x naught of g of x? And we don't even have to use the definition of these limits to prove this fact. We can actually use the previous laws. So let's take a look here. F of x minus g of x is the same thing as f of x plus negative g of x. And if g of x is a function, then we can just say negative g of x is also a function. And in this sense, right, we have the sum law. So we have the limit as x approaches x naught of f of x plus the limit as x approaches x naught of negative g of x. So this isn't quite what we want in this first equation. But if you saw my constant law video, then you can see that this negative is actually something that we can just take out, move to the front of the limit, so to speak. And this will leave us with the limit as x approaches x naught of f of x minus the limit as x approaches x naught of g of x. So therefore, with that information, we have proven the addition and subtraction law for limits. Thank you very much for watching.